So we started binary phase shift keying modulation in the previous lecture, and I mentioned that we need to represent a 0 and a 1 by two waveforms, which are sinusoids, and we discussed that these two sinusoids differ by the phase angle 180 degree or pi radians. That is why, and if you change the uh, uh, phase of s1 of t by pi radians, you will get s2 of t. If you change the phase of s2 of t by pi radians, you will get s1 of t. So these two, that is why the name binary phase shift keying is given. We can represent these s1 of t and s2 of t in the form of our basis functions, which I discussed in details in my previous lecture. And the given signal constellation, or you can represent s1 of t and s2 of t in Euclidean space. You just need one basis function psi1 of t to represent both of these signals, and we did these calculations that the energy of the signal can be computed by just squaring the signal and integrating it in the given time 0 to capital T in that time period, which turns out to be a square t over 2. Now for today our lecture, our topic is BPSK modulator. We will discuss the block diagram of a BPSK modulator. As you can see in this figure, you have two major blocks, an oscillator and the um, non-return to zero source, polar non-return to zero source, which gives you f of t. We will see shortly what is this f of t, and then you have a multiplier which multiplies the output of an oscillator and the output of the NRZ source, and gives you the product of these two signals, which is a times f of t cos of 2 pi fct, and this is a BPSK modulated signal. This is at the block diagram. Let's discuss these blocks in detail. If you see the NRZ source in the block diagram, NRZ source generates bipolar data stream. So it's a f of t, it's a function of t as shown in this figure. It's a bipolar data stream. You can see the signal waveform for binary data. So when you have the data in the form of 1 0 1 1 0, this is just these waveform binary data. The bipolar data stream is shown for this binary sequence 1 0 1 1 and 0. So you can see figure 3.6, which shows the output of NRZ source for binary data 1 0 1 1 0. The output of NRZ source can be expressed as f of t, which equals small a with subscript I and p of t from 0 to for t 0 to t. F of t can be seen in this figure, which is the signal waveform for the binary data 1 0 1 1 0. Now if you see this one, how do we plot this binary data? Let me go to the next page where this I've shown this block diagram. Now this is your f of t. Our data is, let me draw the data. Our data is 1 0 1 1 and 0, and if you see our NRZ source give us the output, which is a positive 1 for binary 1, then a 0, a negative 1 for binary 0, then again a 1 for binary 1, and another one for binary 1, and then a 0. So this waveform is shown in this figure. And the expression which you can see the f of t is represented, f of t is represented in this form, a sub I p of t. Now it is mentioned that this expression is for the time duration 0 to capital T, right? And ai, if you see ai, it is given that ai is either a plus 1 or a minus 1. So this is just a mathematical representation of this uh, f of t, mathematical representation of the output of binary source. Now if you observe it closely, your p of t is actually a pulse. Now what is p of t here? P of t is just a pulse. You can let's try. I'm just trying to explain this p of t, which is, if you see p of t, so your p of t, is, you can draw your p of t in this form. This is okay. My p of t is just a pulse, a positive pulse from 0 to capital T with magnitude plus 1. So this is a pulse. Your p of t is a pulse, and this is scaled by a sub I. So when you multiply it with a plus 1, when you multiply this pulse with a plus 1, you get the same thing. When you multiply it with a minus 1, because ai can be plus 1, minus 1 depending upon the 0, so you get the negative of this one, which is you can write is this one. You can write it is minus 1, right, up to t. So this is your minus p of t. So ai f of t is either plus or minus depending upon the 1 and 0, the binary, depending upon the binary data. Well, this is our source, this is our output, the NRZ data stream, and if we go to our slides further, the other functional block diagram is an oscillator, and the output of an oscillator can be expressed in the form of g of t. Again, it is a time function, and that is the oscillator, so it gives us a sinusoid, a cos of 2 pi f c t, which is g of t. The BPSK modulated signal, s of t, is obtained by multiplying f of t with g of t. So you can see, as given in this equation, that your s of t is actually the product of f of t and g of t, which is shown as a multiplier in the block diagram. This the product, you can you can just substitute a sub I p of t for f of t, and you get this equation, a sub I p of t multiplied by a cos of 2 pi f c t. And in the next line, well, you can see that it is equal to just p of t is not written in the next line. Why? Because in the above equation, in the above line, you by definition p of t exists only from 0 to t. So below we have just mentioned the time that, okay, our expression can be rewritten in this form, just this is valid for 0 to t. So you can see that p of t is unity, it is 1. So we just we ignore it in our expression, and we simplify our expression in this form, that, okay, our s of t is, we can just rewrite that, okay, our s of t, which is the modulated signal, our s of t, which is the BPSK modulated signal, it can be represented as a I multiplied by a cos of 2 pi f c t. So this is our p of t this exists only for 0 to capital T. So we can rewrite in this form. Again, you can say that okay, AI can be +1 and -1 depending upon the data. So it would further simplify your modulated signal. If you substitute +1, it will be a cos of 2 pi fct. If you substitute -1, you will get minus a cos of 2 pi fct, which is of course s1 of t and s2 of t for your so you this is actually, yeah, either it is s in the form of s1 of t or it is in the form of s2 of t depending upon this ai. So this is your BPSK modulator, and when you multiply these two signals, the f of t and g of t, what actually you get. Now the product is shown over here, the modulated signal. If you observe it closely in the first period, well, you can see 1 0 1 1 and 0, and the data BPSK modulated signal is shown. The data is also visible in this diagram 1 0 1 1 0. So BPSK modulated signal, you can see it's a cos wave. Now how to get this one? Let me show it to you on this. Let me represent it. Okay. Let me show it to you here. We'll go to the next slide, and I'll go to the next slide. So we don't want to insert anything here. So let me go to the next slide, and I'll show you this. Yeah, here it is visible. Now how you can get this figure? If you see, this is the product of cos and the modulated signal, which is f of t and g of t, the product of f of t and g of t. If your f of t is 1, suppose your f of t is 1, I draw it here. For 0, this is t, f of t. For the first interval, if you see your this is your f of t. So your f of t is +1, and your signal, the carrier, we have the carrier which is in the form of a cosine wave. So two cosine waves are shown over here. Two waves, right? This is t. This is t. So two waves are shown over here. So you have one and the second one. So two waves are shown over here. A cosine wave. When you multiply it with the 1, you will get the same thing. This one. Again, in the second time period, your f of t is negative, right? For this period, from here up to here, this is the second. From this is t, this instant is t, and this instant is 2t, and this instant is 3 times t, and this instant is 4 times t, and this is 5 times t. So these are the instances. Now the second time interval t to 2t, if you see, the f of t is negative, so when you multiply some a negative -1, when you multiply this waveform with a -1, you will get this one. You get this one, the second one. So this one, you will get this one. So this is the inverted waveform. Of course, if you multiply it with a -1, you would get a waveform which would look like this, which is an inverted waveform. So you can see that your 0 modulates the signal, and the phase is 180 degree. Now this phase shift can be, the phase transition can be observed at instant t and instant 2t and 3t and so on. So the first one, for 0 to t, you have the modulated signal, which is the same, just cos of a cos of omega ct, and the second bit is 0, so f of t is negative. You multiply it with -1 and your signal is minus a cos of omega ct, which is shown in from t to 2t. Similarly, for third one, again you have 1, so the waveform will be a cos of omega ct, which is shown from 2t to 3t, right? And then you have again from 3t to 4t, you have again a cos of omega ct, and you can see the waveform. This waveform is visible here in 3t to from 3t to 4t. Again, this is a cos of omega ct. And the next again minus a cos of omega ct, so from 4t to 5t, again a negative 1 is multiplied, and this inverts the signal over vertical axis. So you can see this modulated waveform, which is a BPSK modulated signal. So this is how we get a modulated carrier. Here the FC is taken as 2 Hz, if you see, because in one time period you have 2 cycles of the sinusoid for sine wave, 2 cycles. So the FC in this figure is taken as 2 Hz. Let me write it here, because you should be able to draw it. This is for 2 Hz or 2 cycles per second in this figure. It's a very low frequency. Usually FC is not in hertz, it is in megahertz, right? So here it is taken as 2 Hz just for demonstration purpose. Now we saw the BPSK modulated signal, and you can have this modulation process. You can do it in the MATLAB. Just simulate this in your MATLAB. Let us discuss the demodulator. We continue with the demodulator part, and the demodulator in the demodulator we have let's see these demodulator in the block diagram first. So the block diagram of the demodulator is shown over here. You can see the received signal R of t. So the received signal R of t, and there is a carrier block. So with the received signal you have a carrier. Let me show it here so that we can rewrite, we can modify our figure as well. So you can see in the figure the block diagram of a demodulator. You have the received signal R of t. Now this, in the absence of noise and other channel effects, if we assume the channel to be ideal and no noise, your R of t will be exactly your R of t is the signal which is transmitted from the transmitting end, and that is a cause of your S of t, which is the BPSK modulator signal, which we have seen previously. So your R of t, essentially your R of t would look like this signal. Your R of t is actually S of t here. Now keep this in mind. Your R of t is actually S of t, which you transmitted. Now we are ignoring the noise and the channel effect right now, just assuming an ideal system, and then we will discuss the performance in the white noise later on. But let's try to understand this ideal demodulator. Your R of t is S of t, which we just saw. And the first thing is the CR block. CR is actually the carrier recovery block. We are not going into details of the carrier recovery block, because you already learned this carrier recovery in your previous course last semester. Here we assume that the carrier can be recovered from this signal, and the carrier is cos of 2 pi fct, which is the carrier, the sinusoid. we can recover this carrier from the received signal. So here we will assume that the perfectly synchronized carrier cos of 2 pi fct is available, and the next block is a multiplier block which multiplies the received signal with the cos this carrier, recovered carrier. Now this product goes into an integrator. So you have an integrator here. This product goes to the integrator, and integrator will here, this is our integrator which integrates this product, and the output of the integrator is given to the threshold detector. So this part is a threshold detector. This is your threshold detector. Threshold detector. So this is your threshold detector. And after the threshold detector, you get the signal is detected as a 1 or a 0. Now just concentrate over these signals. Now let me show you in the slides, and we will see the details of these each and every block. So if we go to the demodulator part, the carrier signal, the output of the carrier can be represented as C of t, which is shown over here. The output is C of t, which is cos of 2 pi fct, right? This is the output of the carrier recovery block. Now we have the signal R of t, and the product goes to the integrator. So what the integrator will do, the output of the integrator is represented by small l in the figure. If you see over here, this is small l. So this small l is the integration of the product. So this is the integration of the product, and the integration of the product from 0 to t can be represented by this equation. So this, the integrator block integrates the product C of t multiplied by R of t. It integrates this one in from 0 to t. So let's solve this integration from 0 to t. If you go through this integration part, let me show it to you here. We can okay, let me represent this integration part. Let me integrate this signal. So we have L, and this L is actually the, now if you see over here, you have it is from K capital T to K plus 1 times capital T, and you have the product R of t multiplied by cos of 2 pi fct, right? This is the output of the integrator. What this k is an integer which is just used for representation of the representing the integral over one time interval. So for k0 it would be from 0 to capital T. For k1 it will be from t to 2t, right? So when so you can substitute k0. Now by substituting k equal to 0, we can write the output of the integrator L, which is 0 to capital T, the integral 0 to capital T a sub I capital A cos of 2 pi fct cos of 2 pi fct for, now this is the output, this is our signal S of t, and this one is the output of the carrier recovery block. So this product is can be written for the first time interval, and if you integrate it, what actually you get is a sub I a, and then you have 0 to capital T cos square 2 pi FCT. Okay. Now if you integrate it using your identity, cos square of theta is 1 plus cos 2 theta over t. So if you integrate this one, you would get a sub I a 0 to till t 1 plus cos of 2 times 2 pi FCT over 2, right? Well, this integral dt, right, dt over dt. So this integral can be expressed, this can be written as ai. If you try to integrate it, this is ai t over 2. Now this is the output of the integrator. Now you know that this is either plus or minus depending upon the 1 or 0. So when it is plus, you will get when ai is positive, when this is positive, right, when ai is positive 1, then your L will be a times t over 2, which is a positive value. A, t into all are positive values. And if this is negative, then your L will be minus a times t over 2, right? Okay, you can always multiply, you can always amplify the output of your carrier recovery block. For example, if you want this to be now before discussing this one, let me clarify that if you have this is either positive or negative, right? So your L is either positive or negative, and then you give it to the threshold detector. So the threshold detector is as it is shown in this figure. This is the property of a signum function. If you learn the signum function, it's shown over here. The signum function, it gives you -1 for all values, for all negative values, right? From if your value is less than 0, it would give you -1, and if it is greater than 0, it would give you +1. It's a property of a signum function. So just try to go through the signum, try to learn the details of a signum function, which is S I G N, signum function, right? And what the signum function would do, that if you have anything negative, it would output the signum function. I think it is SIGN. It is just this built-in function. If you have a signum function and you operate it over a vector, for example, -1, 0.1, 0.3, like this, right? So the signum function would output a vector which will be -1, and for 0.3 it will give you +1. So it would give you this vector. For any negative value, it will give you -1. For any positive value, it will give you +1. So it's actually the threshold detector detects a 0 and a 1, and you get the value of a 0 or a 1. It tells you whether the received signal is 0 or the received signal is 1. So if we see, if you observe this figure, which is the demodulator, we have this threshold detector. Now you can always multiply your the your carrier, the carrier which you have recovered, you can always multiply this carrier by, for example, if I multiply it with a over here, if I amplify my signal with a, what will happen? Now if you go to the integrator part, what will happen? You will get a over here, right, in this integral, and you will get a here. I have to write a, right? I have to write a here, and then a, this will be a square, it will become a square, right, a square, and you will have a square here, right, you will have a square here, and similarly you will have a square, you will have a square in this part as well, a square and a square. Now a square t over 2 is actually the, now just amplifying the carrier, the recovered carrier by a gives you this expression, the output of the integrator, which is actually equal to the energy. If you see the energy of your signal, it is a square t over 2. So multiplying by a constant is just like amplifying your signal, and you would get the energy of your signal here, a square t over 2. So that this is how the demodulator would work. Okay, let me go to the demodulator block. So we discussed the detection process. Here the threshold detector gives you the information that whether the received signal in the given time interval is a +1 or a -1. So it would be a 1 or a -1. It would decide, it would declare it a 1 or a -1 depending upon the value of L, the product, the integrator output. Now we haven't discussed the threshold. What should be the threshold? The threshold, well, we leave it to the later sections, because the threshold detection and the optimal value of the threshold has to be decided, but that would be discussed later in the later part of this course. So this is how the BPSK demodulator works. You have the let me review it briefly now. You have the received signal, the carrier recovery block. The carrier recovery block gives you the carrier of the carrier from the received signal, which is cos of 2 pi fct. You can always multiply that carrier by a or any other constant to get a feasible expression in the end. This product goes to the integrator, which integrates the product and gives you a value L, which is some number, either it is positive or negative. When it is positive, the threshold outputs a +1. When it is negative, the threshold outputs a -1, which is representation of a 1 or a 0. So if you get a +1, a waveform which represent a +1, you would get +1 in the end of this at the output of the detector. If you received a waveform which represent -1 or represents a 0, you would get the output which is -1 at the output of the threshold detector. And this is how the ideal demodulator works. We will add noise into it, and we will see how we will see the performance of this demodulator in the presence of noise in our later sections. Now I would leave this exercise to you people, that find the correlation coefficient of S1 of t and S2 of t. So you should be able to find the correlation. Just find the product when you need to find the correlation coefficient, you just need to when both of these signals perfectly overlap, completely overlap, you just find the product and find the correlation. Correlation will be -1, but you have to find it out, right, in your notebooks. The second question is to determine the signal energy of this. The S2, this signal is given in Euclidean space, which is minus under root e comma 0. These coordinates are given. You can determine its signal energy. So try to represent this in the form of basis functions. Try to represent it as a in the form of basis function S2 of t, and then square and integrate the signal, and you will get the energy of the signal. So our next topic will be array phase modulation. So I'll end up over here. This is for today's lecture.